Hi, I am Thomas and I'm presenting our work Meta-Learning of Neural Architectures for Future Learning, which is joint work with Benedikt and Hendrik. In the typical future learning setting, many related tasks need to be solved, for example different image classification tasks. However, each of these tasks comes with a very limited amount of data. One approach to tackle this problem is via meta-learning. We are on top of solving each task. There's an additional meta-learning loop which tries to leverage knowledge across different tasks in order to improve the task learning process. One example for this would be model-agnostic meta-learning by Chelsea Finn et al., where the goal is to learn an initial set of weights for a neural network architecture, which can be quickly adapted to new weights for new tasks. On the task learning level, a task loss is optimized via gradient descent, and then a meta-learning objective is defined, for example, the sum over the different task losses, which is again then optimized by gradient descent. Note that these optimal parameters for each of the different tasks are part of the meta-learning loss, meaning that for updating the meta-learning loss, one need to differentiate through in the task learning process. As such, meta-learning methods are agnostic with respect to the neural architecture used. It seems natural to optimize this neural architecture, which is also known as neural architecture search. One simple approach to this would be to simply apply neural architecture search on top of meta-learning, as also done in prior work. However, this introduces yet another level of hierarchy. Instead, in our work, we propose to fully integrate neural architecture search into the meta-learning loop. On a high level, within the task learning process, we simply replace the updates to the weights by a gradient-based neural architecture search method to not only update the weights, but rather also the architecture. In the second step, on the meta-learning level, we do not only update the weights, but rather also the architecture. Note that this method is essentially agnostic with respect to the neural architecture search method used, as well as the meta-learning method used. Our method starts with initializing a one-shot model, which is typically employed by gradient-based neural architecture search methods. This one-shot model contains all possible operations such as convolution or pooling. The one-shot model is then meta-trained to yield a meta-learned architecture. This meta-learned architecture can now be adapted to different new tasks, yielding task-dependent architectures. Note that this is in contrast to prior work, which typically optimize for a single best architecture suitable for meta-learning. Unfortunately, these task-dependent architectures will not be sparse by default, meaning that they still contain all the possible operations from the one-shot model. This can be disadvantageous for many applications that, for example, need to be run on limited hardware. Ideally, these task-dependent architectures should be sparse, meaning that they only contain all the essential operations. Typically, a sparse model is obtained by simply pruning the one-shot model. Unfortunately, this leads to a significant drop in performance, meaning that the pruned model needs to be retrained. This can be very expensive in the context of meta-learning, as this would mean that the whole meta-training process needs to be rerun. To avoid retraining, we essentially propose a different parameterization of the one-shot model that enforces sparsity after task adaptation. In the first step, we make sure that from all the possible operations, only exactly one is still active after task adaptation. However, this one-shot model is still densely connected, which might be suboptimal. Therefore, we propose a second modification to also enforce sparsity over the connectivity pattern. In an initial experiment on CIFAR10, we saw that with our parameterization, we can essentially prune the one-shot model without any drop in performance. In the first very controlled experiment, we compare discovered architectures by our method to the original reptile architecture as well as architecture found by Autometa, which is running neural architecture search on top of meta-learning. Our method yields competitive or better results on standard few-shot learning image classification problems, whilst also being more than 10 times more efficient than Autometa. In the second experiment, we do not only compare our method to other methods that learn an initial set of weights, but rather also to other state-of-the-art feature learning methods. Our method yields competitive or better results than the state-of-the-art, while employing a much smaller neural network architecture. To conclude, we showed that gradient-based neural architecture search methods can naturally be combined with gradient-based meta-learning. We also propose a soft pruning strategy of the search model in order to overcome the need for retraining.